Section 5.5, multiple angle and product to sum formulas. Okay, in this section, there's a whole bunch of formulas involving trigonometric functions in various different combinations. And I'm sure you're going to ask me, do we have to memorize all these formulas? Well, my answer is no, you don't. You certainly can if you want to, but all I'm going to require you to do is to be able to use the formulas when you have them in front of you and to remember that they exist. These are the kinds of formulas that you may or may not run into situations where you're going to use them in the future after you get out of this class. And so if you do have a use for them, then you can go back and look them up and use them. And if you're going to be using them a lot, then you can memorize the formulas that you're going to be using. Or if you run into a situation where somebody else is working through a problem or a proof or something, and they use one of these formulas, you'll be able to say, oh yeah, I remember seeing that formula, instead of, huh? So I do want you to remember that these formulas exist, that you can look them up, and that you can use them if you need to, if you have a situation where they apply. So first, some double angle formulas that apply when you have the sine or the cosine or the tangent of 2 times an angle, one angle that's twice as big as another. So in all of the formulas that you're going to see in this section, the U's just stand for any particular angle or expression. So you can substitute in place of U either a particular number or some other expression, an x or a theta or a 5 theta or whatever. Now these double angle formulas can be derived from the sum and difference formulas that we looked at last time. For example, to show that the cosine of 2u is equal to cosine squared u minus sine squared u, we can start by saying, well, 2u is just the same as u plus u, and when you write it that way, it's the cosine of two things added together. The cosine of u plus v, except that the v is just another u. So using that particular sum formula, the cosine of u plus u is equivalent to the cosine of u times the cosine of u minus the sine of u times the sine of u. And then the cosine of u times the cosine of u, well, that would be the cosine of u squared minus the sine of u squared. And so that proves the top line. Now, if we wanted to show one of the others, like that that's equal to 1 minus 2 sine squared of u, we could use the Pythagorean identity, sine squared plus cosine squared equals 1, so cosine squared would be equivalent to 1 minus sine squared of u. Minus another sine squared of u would be 1 minus 2 sine squared of u. So there's two, or actually 3 different things that cosine of 2u is equal to. So depending on the situations, if you have a cosine of 2u showing up somewhere in something you're working with, you could replace it with any one of these 3 other expressions. Let's test this one out on an angle that we actually know about. This should apply no matter what u stands for. So let's try plugging in 30 degrees. If u stands for 30 degrees, then 2 times u is going to be 60 degrees. And we happen to know, or at least I know, if you don't know it, you can look it up on the unit circle, but I happen to know that the sine of 60 degrees is exactly the square root of 3 over 2. And that the sine of 30 degrees is exactly 1/2, and the cosine of 30 degrees is the square root of 3 over 2. And when you work it out, the two sides of this equation really are equal to one another. They both turn out to be square root of 3 over 2. So at least for that particular angle, that shows that this does hold true. Now, it holds true in general, but that just reassures us that, okay, there's an example where the two sides really do give you the same number. Now let's do some more examples working with these. If we start with 1 minus 2 times the sine squared of pi over 10, do you see anything up here on either side of any of these equations that fits this pattern, that looks like 1 minus 2 times the sine squared of something? Yeah, 1 minus 2 sine squared of u is equal to the cosine of 2u. So that's exactly what we have here, but in place of u, we have the number pi over 10. So that formula tells us that this is equal to the cosine of 2u, so 2 times pi over 10, or pi over 5. So 1 minus 2 times sine squared of pi over 10 is equal to the cosine of pi over 5. How about 4 times the sine of alpha times the cosine of alpha? See anything that looks like that? Well, this right here, 2 sine u cosine u, looks a lot like this. There's a u in place of an alpha, but remember the u can stand for anything. And there's a 4 out in front, where in the formula there's a 2, but we can take that 4 and break it up into 2 times 2. So we can think that this is 2 times the sine of alpha times the cosine of alpha. Now, temporarily ignoring that 2 out in front, the rest of that is just 2 sine u cosine u, with the part of u being played by alpha. So that's equivalent to the sine of 2 alpha. And then we did have that 2 out in front, so this is 2 times the sine of 2 alpha. And what about 10 times the tangent of 3 theta over 1 minus tangent squared of 3 theta? See anything that fits that pattern? Well, it looks a lot like 2 times the tangent of u over 1 minus tangent squared of u, but in place of u, we have 3 theta, and the number out in front isn't 2, it's 10, but we can break that 10 up into 5 times 2. So it's 5 times 2 times tangent u over 1 minus tangent squared u, with the part of u being played by 3 theta. And so the 5 just stays out there being a 5, and all of the rest of it is equal to the tangent of 2u, except, like I said, the part of u is being played by 3 theta, so 2 times that would be 6 theta. So we've simplified this to 5 times the tangent of 6 theta. Now let's verify some identities with the help of these double angle formulas. Remember how when you are verifying a trigonometric identity, the way that works is you start with the expression on one side and you change it one step at a time to try to end up with the expression on the other side. So here, if I start with the expression on the left, I can change that by replacing the cosine of 2 theta with what it's equal to. I can replace it with any one of these 3, but the one that's going to be most helpful is to replace it with 1 minus 2 times the sine squared of u, but in place of u we have theta. So 1 minus 2 times the sine squared of theta plus 2 times the sine squared of theta. And then the minus and the plus cancel out. This is equal to just 1. How about this one? Cotangent of theta equals 1 plus cosine of 2 theta over sine of 2 theta. So start with the expression on one side. If I start with cotangent of theta, the only thing I can think of to do with that is to write it as cosine over sine. Cosine of theta over sine of theta. Now, right now, on the bottom I have sine of theta. I want the sine of 2 theta, which is equivalent to the sine of theta times a 2, and a cosine of theta. So if I had those other factors as part of my denominator, then that denominator would be well on its way to looking like what I want it to look like, sine of 2 theta. So I'm going to multiply by 2 cosine theta on the bottom and on the top. That way on the bottom I get 2 sine theta cosine theta, and on the top I get 2 times cosine squared of theta. So just like I said, the 2 sine theta cosine theta on the bottom turns into or is equal to the sine of 2 theta. And then on the top, we have 2 cosine squared of theta. Well, that's almost like the right side of one of these double angle formulas. If it was 2 cosine squared theta minus 1, it would be equal to the cosine of 2 theta. It's just 2 cosine squared of theta, but I can add 1 to both sides of this equation and say, okay, that's equal to the cosine of 2 theta plus 1, and we have reached our goal. And how about this one? The tangent of theta plus the cotangent of theta equals 2 times the cosecant of 2 theta. Okay, if I start with the left side, tan plus cotan, tangent of theta is equal to sine theta over cosine theta, and cotangent of theta is equal to cosine theta over sine theta. Now let me get a common denominator so that I can add these fractional expressions together. If I want these to have the same denominator as each other, I've got to take the first fraction and multiply by the missing sine theta on top and on the bottom, and take the second fraction and multiply it by the missing cosine theta on top and on the bottom. And now that they have the same denominator, I can combine them into sine squared theta plus cosine squared theta all over that common denominator, sine theta times cosine theta. Now, famously, sine squared plus cosine squared is equal to 1. And so now I have 1 over sine theta cosine theta, and if that had a 2 in front of it, I could turn it into the sine of 2 theta. So to get a 2 in front of it, I just multiply top and the bottom each by 2. So now on top we have 2 times 1 is 2. On the bottom we have 2 times sine theta times cosine theta is the sine of 2 theta. And the reciprocal of sine of 2 theta would be cosecant of 2 theta. So we have gotten what we wanted this to come out to equal, 2 times the cosecant of 2 theta. Now here's an equation to solve. Cosine of 2 theta minus 11 cosine theta plus 10 equals 0. To start with, I'm going to take this cosine of 2 theta, because it doesn't really match the cosine of theta, and turn it into something that does just involve the cosine of theta. Replace it with 2 times the cosine squared of theta minus 1. Now, after a little bit of combining like terms, this looks like a quadratic equation where the variable that's being squared is cosine theta. If I let u stand for cosine theta, then it does look like a quadratic equation, and I can solve it by factoring. U is equal to either 9/2 or 1, and since u is really cosine theta in disguise, that means cosine theta equals 9/2 or 1. But if cosine theta equals 9/2, there's no solutions for that, because cosine can't be greater than 1. And if cosine theta equals 1, the only angle whose cosine is 1 would be either 0 or something that is equivalent to that once or more than once around the unit circle. So 0 plus any integer multiple of 2 pi. So for this equation to be true, theta has to be either 0 or 2 pi or negative 2 pi or something like that.